this is about multiple RAG last week. Yeah, first question is about X. Great. Most people got this right. Thanks. Okay, now it's on there, right? Okay. So we have Nora at the top of the leaderboard, followed by Lewis and T. Okay, so this is about the threshold concept. Why might we have so this appears that a lot of people got this not correct. So this is not actually for a rear anchor. We kind of discussed this a little bit in class last week, where we said that the distributions for different modalities are a bit different. So you need like a different low confidence cutoff, and that's the blue option. Yeah. Oh, and overfitting is also like kind of a red herring. The threshold term does not have to do with overfitting. And now Sai is at the top of the leaderboard. Let's go to the next one. So this is about granularity mismatch. You recall this is like a equal distribution, red, blue, and yellow answers. So granularity mismatch is basically like if you ask for, you might want to ask for like a very specific thing in an image, but if you just go by the words, it might retrieve like everything that's relevant. So like everything with a person or like a red curve or what. So you might get the entire image when you're only looking for like a subset of the image. So that's the red option. And Sai is still at the top of the leaderboard. So fine-tuning to re-rank is one of the ways that we can. What is it actually? Yeah, and it is basically a cross-encoder. And the reason for that is essentially you want to match the words, the query to the various multimodal items. And you want to basically fine-tune on the relevance score on that one. So that's the part that you would fine-tune, not the generator or the LLM. Next question. Oh yeah. Luis is now in top, followed by Estelle, Sai. Okay, so the next one about clip. So how do you get them bound together? I guess this was not very difficult. Yeah, contrastive loss is the technique that we use to push things that mean that have similar meanings, but in different modalities. We push it together. Yeah, and the next one. So Estelle is now at top the leaderboard. Give a bit of a shake up. Yeah, this is more about the training. Okay. I guess this was not a very difficult one. Yeah, so a negative example is when we pair something with an unrelated image, so that to show that it's not related. And the last question now. This is a bit of a curveball. Pick the blue option, but predict how ChatGPT would answer this question. So I bet this is the ChatGPT earlier. Yeah, faster with it. How is it gonna interpret this multimodal question? Okay, so we have the split. A lot of people thought it would be based on the text that's in the image, but as it turns out, the option that ChatGPT actually picked was based on the blue box in the image. And that we have Louis at top, followed by Estelle and Zai.
All right, let's give a hand to all of our participants. And hopefully tell us so that helps us together this day. Thank you.
I think
Okay, great. So intro continue. So I have some quick announcements. First. So again, every week we're going to go through a little bit of the Slack and again in the projects. You should have all told me that your round 3 sprint is finished. So this week it's week 11, so it's the due date for round 4. So we are not. So that means it goes in. You guys are late on turning things in, and I'm late on creating them. So there's fair, right? So I will get towards putting comments in. Hopefully, you can all those or some other things too. I would talk about that. Next thing is, of course, it's graded, right? So 30 times flash. Just make sure you're putting the effort, right? But we really want to get hands-on time. Make sure you and then you have enough. That's the part because we will have people from the general public. We actually have people here in the general public who will attest to people who want experience working with GraphRAG. You know how it goes. Like they'll say they need like 5 years of relevant experience GraphRAG. Right? Great. Sad. But you can say that you have experience. So again, go to your projects. If you have your thread already in one of these, then you should have had 3 next to them. Some of you only have like 1 and 2. So a bit of trouble here. We need to see at least a 3 or a 4 there soon. So please get them in. I actually do all of these books. Tell me, let's say JF teammate what they've done. Sure. And actually, if anybody read use as a 1 and a 2, you go on and set the 3, but I've created it, then I will share it. Okay. Separately from that, you already know the 27th step coming up. So okay, so right here on front. Roughly 2 weeks from now, right? It's 13 days from now. You would have 27 steps. There will be an MPSS speech in concrete. So of course, many of you have been doing what it's like. So if you haven't been, it'll be a lot of fun. It'll go from Wednesday afternoon. As I said before, in the general channel. After week 13 on Wednesday after steps, after our course is finished, it'll actually probably finish close to pretty slow. Hopefully they'll finish on time. Then we will go someplace. You want to join right here, otherwise it's also the so you put your hand up here. The rest of you have to put your hand up channel random channel, that's fine. Just a thing for that and sign where to go. You guys have interesting ideas about where to go. It's not too hard. What's this week 13 for studying finals? Just write a message. All right. So please do that for us and make sure in our sheet that you have continue to update these columns. So you're listening to this now. So hopefully you can go to look at weeks 8 through 10 and write down the hours and like see that that shouldn't get it, but not the hours. You have not put up. Okay. What we need to see is by the end, and then you have spent at least 70 hours if you are in CP, if you want to wait 8, and then 130 hours. Try to be as simple as you can with your hours and put it right about the time. So for example, 30 hours, that's a bit of a stretch, right? Spent for 24 hours just prepare for about 10 minutes lecture. That may be a bit too much. So, generally, when we go to the roles document, we'll have to note it what I have specified as okay. If you think that you really did spend an hour, then basically what I'm looking for is sufficient number of time on projects and preparation, and of course, around 10 to 15 hours at most. Okay. Your lecturers, on the other sense, spend a lot more time, right? Like you have to prepare 2 hours lecture, roughly 10 times.
Only lecture twice. Only lecture twice.
Yes, so there's 2 lectures, right? So there's a lecture 1 here and a lecture 2 here. So he says he spent 60 hours.
Actually, I actually meant to do like 30 overall. I ended up adding 30 each.
Okay,
Yeah.
so you can correct it. I mean, I'm not trying to call you out, although it's video recorded and everything, but yeah, you can get notoriety. So yes, you are honest, you are right. The external participants can come to steps. So what you do with that is you can register. I think there's this nice big new button register here, and then you can fill that out. Hopefully it is actually working at some point, and then you just show up. Those of you in the class already, your names have been given as our project participant. That means you're already people out there again. But if you want your project to win a prize against usually more of a popularity contest, get your friends and people to vote for you. Usually it's some version of Comp Club. Okay, but yeah, we know it's not necessarily the popular prizes that are the best environments, but do spend time. The last thing I'll say is we have a guest here today, Alice Galatros, the professor from University of Lausanne. But he's also an information retrieval professor, just like Yu Haitao was. Yu Haitao was with us for the first half, professor on that. And Alice is working on a digital library project, Apple Vision Pro to visualize that type of stuff. So you can talk to them about OCR and RAG, the CSAT RAG, the documents from the teacher library, take document queries, talk about them. Yeah. Please welcome to our course today. Okay, with that, we'll go on to the regular. So just to make sure you guys are already here. See, 6101 is here. So these are all of your project names for us. So of course you don't have posters yet, but as you start to get things down, they like project name. Please put it in an abstract. You can see some of the other courses they've actually used the game development, of course, they always put a lot of that. Okay, so with that, I think you can start like okay, so and we have Indra, Luis, who is online. Zizhen, it's also not here, so I guess that's online. Van-Hoang is my former student, so he online. And Hong, are you here? Oh, yeah. Okay. All right. So you're presenting last, is that right?
I think
Second. Okay. You're both round. Okay, great. So without further ado, I'll ask you to start. Please, if you're lecturing in class, and make that the annotation shows up better, and try to speak in a little bit of a louder voice so that my ceiling pick up. Okay. All right. So we're good. You guys on remote can see us, right? And see the slideshow. Let us know.
All right. Hi, everyone. I'm Indraneel, and today we are going to talk about GraphRAG. We get oriented, right?
We drag far.
So, cool. So today I'll be first introducing GraphRAG, and then we'll go deeper into it with graph data source, query processor, retriever, and other stuff. In my section, I'll be talking about a survey paper that basically gave us that overall structure that you saw. And I'll also be introducing two main papers in GraphRAG, which is the original GraphRAG 2024 Microsoft paper, as well as the LightRAG. The interesting thing about GraphRAG is that it's actually so recent. Like the Microsoft paper was just last year. So what is GraphRAG? It's essentially structuring information as a knowledge graph, and then you traverse it during retrieval. We all know what graphs are. They kind of look like that. And yeah, and you want to see the reference for this survey paper that's below here. So yeah, so let's do a bit of a Git interactive mode here. Let's collect some answers to get a little bit of intuition on where we are, where everyone is in terms of GraphRAG. So why do you think that we would want to do GraphRAG? Why GraphRAG as opposed to like normal RAG? What's in your mind?
Maybe connection across multiple concepts. Like if let's say you have a thing that you want to get A to B, but you need to go to B and then B negotiate that B, then not like multi-hop, then you can be good to have GraphRAG first. Then even when you retrieve, you can also kind of see that pathway. It also helps you.
Vector space embedding, I think you'll see the semantic similarities. They miss out on all these that are available.
There are just multiple types. I need hypothesis to be given.
All right, cool. So yeah, one of the common themes that I hear is like connections, and that would be right. Like sometimes, the way that we think in our brains, like we don't necessarily work in terms of like PGSQL tables. Maybe we think of ideas as being connected like different webs. So GraphRAG is kind of a way to model that. But yeah, so some limitations of vanilla RAG give rise to trying to create GraphRAG. And one of them, as you guys have alluded to, might be fragmented answers for multi-hop question. So an example of a multi-hop question is like, how does the rise of electric vehicles influence urban air quality and public transportation infrastructure? That's like two different concepts that are involved here that have to be connected. So GraphRAG might be better for that. We're missing like global high-level overviews in like regular RAG. Because it will just retrieve the information specific to the content, and finding themes might be harder. And relational info is not explicitly captured. So the nature of GraphRAG is that the nodes are the entities and the edges are the relationships. That's how we encode the information. So given any text, we would try to break it into entities and relationships. And these relations are also like directional. And the directional nature becomes useful in the kind of queries and tasks that we want to answer using GraphRAG. So the example here is like, for example, if you're talking about finding the connection between epithelioid sarcoma and some drugs that affect like maybe this like EZH2G, you can traverse it, get the neighbors for the disease entity, and get the neighbors of the gene product entity, and then after that, like do the intersection. That way you can find out what's related here. So it might be suited particularly for things that have graph structures naturally. So one example of that is like social networks. We see that like Facebook and stuff, as well as an interesting one from this review paper that I never thought of was molecule graphs. So molecules can be represented as graphs, and it might be actually very useful to traverse the things that make up that molecule in that way, as well as product taxonomies. Basically, this refers to like having 1,000 layers of menus in like a Amazon website. You want to talk about how websites are structured, that could be a product taxonomy. So continuing, like saying, trying to define it more formally, what's the nature of GraphRAG and how does it differ from usual RAG? The first difference in this survey paper is basically the unified versus the diverse formatted nature. So what this means is that usually info can be represented in terms of tables or 2D grids, but sometimes when the information is diverse, it doesn't follow the same format, then you might want to connect it using GraphRAG. Also, independent versus interdependent information. What this means is basically if information depends on each other, it's interdependent, then it might be better to use GraphRAG. The third point I will talk about in my next slide. So that brings about also some challenges. One of them, an easy one that you might think of, is that constructing large graphs might be computationally expensive, because you might have to, especially if you want to do a fully connected graph, and you have already have 5 million documents or something that you want to put in. Graphs may not be dynamic. What this means is if you try to add new information and you've indexed the graph once, you might have to index it again. And then that could be very expensive. You don't have ways to do it efficiently. And also, yeah, so the third point is the third point from the previous slide as well. Graph structures could be very case specific, and therefore GraphRAG need not be very portable. So an example of this is if you consider the structure of nodes like airports that are hubs and spokes. Airports that are hubs are not generally connected to each other. So that's not really the case in like another example, another domain, which would be that a similar node type is connected to each other. And that happens more in like academic papers. So a graph structure that you get from maybe like an airport network would not be mappable to one for academic papers. So the framework that this survey paper introduces tries to group or look at GraphRAG in this manner. There's a query processor at first. So the purpose of the query processor is basically to process the query. There's several things that go on in there. I'll speak a little bit more about them, and the subsequent presenters will speak a lot more about them. Also, like the retriever, what this does, that's to do with retrieving the index or saved information. And then sometimes, as we've seen in the pattern that exists in RAG, just retrieving the information is not enough. You need to often like re-rank it, organize it, pick the key parts, and then finally put it into the LLM and generate the information and answer that you're actually looking for. So yeah, and the paper also tries to find a group, make a grouping of the data sources that are pretty common. And the examples of this include everything from knowledge graphs to usual knowledge graphs to like special cases, document graphs, social graphs, scientific graphs, planning graphs. So planning graphs would be really useful in like agentic paradigms that we see today, as well as infrastructure, scene, not sure what that is, tabular and biology. Oh yeah, and also random.
For the scene graph, like a graph based on a natural, right? You want to know where objects are concentrated to each other, like demand is less than the table.
Okay, that's true. Yeah, so what might be some considerations that might be involved in graph construction? So the first thing that we have to do regardless is that we have to extract triplets because you have the entity relationship entity pattern. So this can be rule-based or large language model-based. A lot of techniques, especially like the Microsoft GraphRAG and the LightRAG method, they use a large language model to basically generate the triplets. That's probably the easiest, but arguably it is kind of expensive because if you're relying on a large language model to generate your triplets, it has to go through the whole process of attention tokens and all of that. Also, like when you have complex queries, like please generate an image where a girl is reading a book and her pose is the same as boy, blah, blah, blah. That you might want to decompose that query into subtasks and then hand it off so that you're doing less at each step. And query expansion is kind of like augmentation. So yeah, so these are the two papers that I've been talking about. So I'll go deeper into them now. So Microsoft GraphRAG, the original one. So this is built for sense making. So what is sense making? It's basically the definition of sense making is trying to queries that basically try to give a global understanding of the entire data set. So that includes like trying to identify trends or being able to summarize the data and see broad themes across it. So that was the focus of the GraphRAG paper. And the method that they use, first they use an LLM to create the triplets, then it forms the knowledge graph. After that, we partition the graph to a hierarchy of communities. And then you use the LLM to generate summaries for those communities. So these summaries are generated from the lowest level and then recursively upwards. I'll explain this a bit more later, I'm also going to show the exact algorithm to find the communities. So when you recursively incorporate the lower level summaries in the higher level ones, it kind of includes the information from below. So at query time, it uses a map reduce step where you pick information from the summaries and you aggregate it together, and then you give the answer. So this is a diagram of what I just explained. So if you follow the flow here, there's indexing time and query time. So you have the source documents, you do the text extraction and chunking. And then once you have the chunks, you do the entity extraction, and then you form the graph. And then you have the knowledge graph. Then once you have the knowledge graph, you then want to partition it into communities. And then you get the community summaries. Then you attach it to the graph. And then when finally you need to work on it with your query, you grab the related paths and then give the answer. So how did they evaluate their method here? So they focused on sense making. So they kind of used an LLM to produce a bunch of questions and answers. And all of these questions and answers are meant to be high-level questions and answers, as per the definition of sense making. And then they tried to evaluate how GraphRAG was able to answer these high-level questions using the following criteria. There's comprehensiveness. How much detail does the answer provide to cover all aspects, details of the question? There's diversity. How varied and rich is the answer, as well as empowerment. And how well does the answer help the reader understand and make informed judgments about this topic? So as you can see, these are kind of subjective. I know that they have a little more in terms of the criteria, but I have not shown it here. But it is arguably a bit subjective. So to critique this paper a little, in my opinion, they circumvented using established QA datasets like Hotpot QA by citing a focus on sense making. So by citing a focus on sense making, they said we're not going to focus on like the multi-hop kind of queries that we might have. So it does not test its ability on multi-hop reasoning, and instead kind of just focused on this summarization ability. So, I think based on the other works that exist, there's scope for GraphRAG beyond just summarization. Actually, our group is kind of trying to explore this as well. But yeah, then we move to the light RAG, just kind of an augmentation, an improvement on the GraphRAG that was introduced earlier. So the method for this is also to use an LLM to extract the entities and the relationships. And then after that, they do this method called LLM profiling, where you have the keys and the values, and the entities are the keys, and the values refer to the text that is associated with that key. Then after that, you need to do some kind of deduplication in constructing the knowledge graph, because if not, the graph grows complex and it's not very efficient. The main difference with GraphRAG is that there's no community summary here. Instead, they kind of do this I don't know if it's inspired from thinking fast and slow or not, but they have this high level and low level kind of query. So when you pass the query, it will be turned into kind of a high level abstract question, and also a very specific low level question. So we get those entities, and we get both the high level and the low level entities, and then we search the graph based on that. So that's how we grab the information, and then we put it in and give the answer. So this is the diagram that explains what I just talked about in a bit more visual manner. From here you have, like, on the left you have the text, and then the first is the indexing process, where you grab the high level, you grab the entities, and then this is the key value pair, where the value is the information associated with that entity. Then you make it into a knowledge graph, and then you have the at query time. You turn the query into low level keys and high level keys, and then you extract the necessary information. So earlier I spoke about the community finding algorithm. So how does it actually find the communities? The way that that's done is using the Leiden algorithm, and that's what I'm going to explain now. So first, like, motivate. Why might we need to do this? So imagine, like, you have a lot of nodes in your graph, like millions or maybe billion. You can't possibly search everything, right? So you need to narrow the search space. So by finding the appropriate community, you might be able to narrow that. So how Leiden works is that you want to maximize this thing called modularity. And what modularity is saying is basically if a community is better connected within the community itself, that's a good thing. You want a community to be highly connected within itself. Then you have found the right partition, because no other node would want to be in another community. So that's kind of where we're trying to go. So this is the function. It kind of describes the same thing. So M is basically the number of edges. Kind of you divide by that, because you're kind of like averaging by that. The K would be the values, the edges, the edge values. And then that term you see on the right with that and the I and the J, that's basically delta, yeah. That's basically saying, like, we only want to consider the stuff that's in the community that you're talking about right now. So it's 1 or 0. So when we have this, how it starts is first you let every node be its own community. And then the first natural step to go from here is you pick a random node and you want to find what community does it go into, right? So that's exactly what we do. Maybe here we can take like 6. We'll compare node 6 with like each of its other neighbors, and we simply check the modularity change. So you want to eventually put it in the community, which gives the highest modularity change. And that means that it is in the community that makes it the most interconnected. So that might result in this kind of situation, where now 7 and 6 are in a community. And then you successively continue to carry out this process until you have visited all nodes, and all nodes have been grouped into community. But at this stage, we're not done yet. We kind of take ideas that similar to like HNSW, and we can repeat this process and aggregate the communities once again. So if you've heard of Leiden, you might have heard of Leuven. Leuven was the first iteration of this. Leiden improved it by trying to do this hierarchical thing. And then you just represent a community as a node again. And then you perform a similar task and you find the higher level community. Yeah, with that, that is the introduction to GraphRAG, overall motivation, as well as the GraphRAG paper, LightRAG paper, and the community finding helpful. Yeah, thank you.
All right, let's thank our speaker. Any quick questions?
Oh yeah.
Yeah,
Just like you mentioned, was molecular. Just wondering whether AlphaFold.
I don't think it's using exactly like that. It's super complicated. I'm not really
Diffusion modeling. So it's using diffusion modeling like a 3D policy.
like AlphaFold.
Yeah.
Oh yes. Maybe.
okay, so if you guys want to find out, we'll put it up. Also, take a look at it, like, there are technologies for facts and uses each. You have a else inside sample ways. And so find and consider in a way that's specific to certain extremes on the whole region. Right, but this one, this is an exact algorithm with deterministic. So when you rerun it, it will give the same results. And as it is a hierarchy of stop clustering and then some automatic side. Other questions? Okay, so that's great. So we'll go on, and I think our next speaker is Tommy.
I'm actually
You're number 3.
Yeah.
Okay. So then I think it's Zed is next. Yeah. Right. So, Zed, are you on?
Yeah, I'm online, but I can't share my screen because.
Okay, we're going to stop screen share, let you take over. Okay, and then you can take off the screen. Share it to you.
Can you see my screen?
Yeah. Okay. So it's all yours.
Oh. Okay, so hi everyone. I will talk about the graph data source component of the GraphRAG framework. So first I will talk about the definition and its importance, followed by some common representation and the storage form. Then I will go through some type of like a graph data source. I will talk about 2 concrete examples of graph data source, which are knowledge graph and a scientific graph. And I will talk about some takeaways and future directions. So the graph data is an external knowledge organized as a graph. So usually the node represents entities and the edge represents relationships. So as you can see from the picture below, in the entire pipeline, the user will first send query to the query processor. The processor will process it and get and put and give it to the retriever, and the retriever will retrieve from the graph data source. So the graph data source basically serves as a memory or knowledge base for the GraphRAG. Unlike the traditional RAG, the GraphRAG have several advantages. First, it can enable the multi-hop structured retrieval instead of flex text search. For example, you can see the image in the right. If you want to ask that what is the nationality of Jack's wife, in the vanilla RAG, you need to find documents saying who is Jack, who is his wife, as well as their nationality. However, if you use a GraphRAG, you can just traverse the graph. For example, you can go from the Jack, then he's married to Jill, and Jill is born in New Jersey, which is a state of the USA. So you can just return the answer. So the advantage is quite obvious. So the graph will make the answer explainable and traceable by showing the entire reasoning path, and it can also reduce the hallucination by grounding the answer in a clear relationship. Lastly, they can handle the complex query by linking multiple facts across entities. And there are several ways to represent the graph. For example, to represent the graph in the bottom right, you can use adjacency matrix like the one shown in the blue, where each row and each column is is a node, and the 1 means they have connection, and 0 means they are not connected. You can also use edge list, which is on the bottom left. So you can store each edge as a tuple. For example, drug A is bind to like a protein X. Also, you can use adjacency links, like the one shown in the green. So for each node, we will maintain a list of its neighbor nodes and the relationship. For example, for drug A, you can store protein X and the binds to relationship, or join Z and the targets relationship. Also, you can also serialize the graph into sequence using like a breadth first search or depth first search. For example, if you use depth first search, it will go from drugs to protein X to join Z and disease Y. However, this process is usually irreversible. You can also store it in natural language. For example, you can just describe using plain text, such as drug A targets gene Z. And the types of graph data source, including like knowledge graph, which are semantic network that can connect several pieces of facts together, like a Wikidata. There are also networks in the real life, such as the citation network, social networks, and or recommendation graph. There are also domain-specific graphs like a biological interaction graph, the roadmap, and something like that. The explicit graph are graphs that with a clear defined edge. For example, the molecular structure already have a clear graph structure, so you can directly use it. Or the citation, if you cite another paper, you directly have a link to another paper. However, for implicit graph, you need to derive it from some data. For example, the word co-occurrence graph and the feature correlation graphs. To construct the graph data source, you can use several methods. For example, if it's explicit, you can use explicit construction if it already form a structural relationship, such as atomic bonds. Also, you can extract the graph from the text. You can have some rule-based parser to extract the entity and the relationship from the passage and organize them into triples, like entity A, relationship entity B. You can also use some encoders to convert existing data format to graph. For example, in medical domain, the molecular representation of aspirin you can convert the one-dimensional smile using the Redic RDKit library and construct and turn it into a graph. You can use some other methods like constructing graph from images and so on. One specific example is a knowledge graph. So it's usually used to connect facts, and the scope can from very general, like the Google Knowledge Graph, to very specific domain, like BioAsk. And as mentioned before, this kind of knowledge graph can enable multi-hop retrieval and traceable evidence and reduce hallucination. Some of the common downstream tasks, including the question answering, fact checking, and so on. To construct the knowledge graph, one common way is use like a manual labeling. It is quite precise, but it is very costly, like a Wikidata. You can also use rule-based method. You can develop a parser to parse a relationship in the documents, but it is quite brittle. You can also use LM-based method, but it will introduce some noise. Another concrete example is scientific graph. Some of the common types, including the molecular graph and the biomedical graphs. And one very important property of this kind of graph is that it can encode some domain constraints or structure constraints that are usually missing from the plain text. And the GraphRAG can use them to retrieve some structural evidence and improve the validity of the LM. Some of the representation of the science graph, including like SMILES, which is for 1D. You can also have 2D molecular graph, or if you introduce a coordination, it can form the 3D graphs. Aside from this kind of molecular structure, in medicine, you can also extract relationship from text, which is just similar to what knowledge graph do. So you can extract the entity, extract the relationship, and form triples. For example, aspirin can reduce inflammation. And you can also use some libraries to convert the one-dimensional strings into two-dimensional graph. And for the three-dimensional graph, you can access some publicly available libraries such as PDB. So in conclusion, the graph data source is the knowledge backbone of the GraphRAG, and the GraphRAG's performance is highly dependent on the quality of the data. And also, the graphic data can encode very rich relationships. This can provide the multi-hop reasoning and the relational context for the LM. Moreover, it has lots of variants. For example, the scientific graph and the knowledge graph. So different graphs may be used suitable for different tasks. And the future directions, including like better graph construction tools and dynamic update of the graph and so on. And I think I will pass to Hongyi for the next part.
Okay, let's thank that for his part of the presentation. We have a little bit of time for questions. Anyone want to ask a question right now, or anyone would like to give any comments? Okay, so if you go back one slide, then mention something very critical, which is that all these graph algorithms only work when there's good graph data. If you don't have good data, you don't have a good graph. So quality of these algorithms really subjectively associated with the graphs, right? Because we've seen in other cases that certain types of relationships, like related to, that could hold for many different types of. Therefore, it may not be a very good type of edge to add into the graph unless you clearly define what related to means, or you have some types of that, right? So that can be in many different types of systems. The relationships, the density of the edges, coverage of the nodes, they make or break our GraphRAG. Right? So in some of the natural graphs that we're seeing in Indraneel and Zizhen points, like for example, a scene graph. A scene graph, again, you can think of like in video understanding, right? So you take a random frame from film or a short video, right? And you ask, what are the objects in this image, and where are things located? How long do they exist for within the video? Between what time to what other time segment? Then you can piece it about things that are on things that you might ask. Something in front of, on top of, sides of the object that contain it. Those are the types of passive scene graphs. Those things also happen in document graphs. So, for example, in Metalysis digital library work, we are concerned about documents that are like newspapers or web pages, right? So these types of web pages or newspapers, they have images, they have captions, they have columns of text, paragraphs of text. So all of those are different units of information that we can stitch together in a graph, right? And then you can query what's the story next to this story. That takes the word, I don't know, graph, right? What is the picture on page 5 that is next to a story on the bottom, right? These are the types of questions. Yeah.
What developer? Thinking, you can take a picture of that. model, it's the DOM considered a graph. It's got the kind of relationship between parent child. Would that be
Yeah, so often a DOM tree is described as a tree, a document object model. It's a tree, but you can always view it as a graph, right? So some of the algorithms that we talked about here is providing extra relations that might be not considered in the DOM tree. DOM tree is usually layout based. Okay, but you can say, for example, I want to link two parts of a DOM together because they share some vocabulary or they share some cosine similarity above a certain amount. Then you add an edge there, and that makes the tree into a random graph, right? So depending on how you see these so usually the DOM tree is the tree just because easier and more hierarchically convenient and efficient to process by algorithm layout, right? That's thanks. Other questions for anyone? Okay, so I think it's Hong-Yi's point, and then after Hong-Yi's section, then we'll take a quick break. So we'll share screen again. Share. Yeah, you can. I think that's it. Yes. Yeah.
Okay, so now I'll talk about the query processor. So first, just as an overview, I'll start with the basically what a query processor is. Then, given this query processor, like you can break it down into many different subprocessors, and then after that, I'll give an example of what it looks like in real life, and like what an output of this query processor might look like. So, what is query processing? So, given that in the context of RAG systems, our data is already in the graph, but then that itself is very difficult to express as raw text. You can't really just throw that into the context window and expect something, because it's kind of a complex data structure. So what can we do is here we have basically only nodes, edges, and eventually paths, right? So the challenge is how do we turn like a natural language question into something that we can use to actually throw at our graph and retrieve something back. So in the paper, they talk about basically the function we call I guess omega processor, and it comes out Q hat. Yeah. So for example, this is relevant in situations. To me, the one that screams out the most is actually multi-hop instances. So for example, which novels are written by the author of 1984. There's a book, there's the novels, and then a lot of information that potentially might come from many different sources. So we need to figure out how we're going to put that information inside graph. So in general, the review paper divides it into 5 different subprocesses, starting with entity recognition, relational extraction, query structuration, query decomposition, and query expansion. If you look at the examples here, I think they're kind of they're kind of obvious and I guess kind of intuitive what each step is really doing. I think that is something that is kind of something you think through when you're looking through a question or you're trying to break down a question to sub questions. That's something you kind of do it either intuitively as a human or like your brain just kind of works that way. So let's run through an example of how an input query might be transformed through this very sequential process that is our query processing. So I'll give a very difficult and complex domain-specific multi-hop question. For example, if I threw this at ChatGPT and say ChatGPT was attached to a RAG system, what would it look like? So I have no idea what this question is really about. And I mean, the example is honestly courtesy of ChatGPT, but I think the walking through it step by step is quite helpful in understanding what the process actually looks like in real life. So we start off with name entity recognition. So honestly, this is really just identifying like what are the actual things in the questions are. So based off the question, initially something's scream out. So for example, the second word cytokines, or like CRP, all these kind of scream out at you, and you kind of need to extract this for graph traversal later on. So I guess this is the first thing you do. Next, you have query structuration. So basically, this converts your question into something that you can later process later on. And I guess it's very unique to how you store your graph as well. So be like SQL or SPAQL to interact with your relational database. So at the end of the day, this allows us to optimize for better retrieval. So I guess it's sort of like context management for your graph. So next, I think this is, I guess, the core of or to me the most important step of I guess the query processing, which is your query relation extraction. Because just like how Prof mentioned just now, how good your graph is basically almost a function of how good your edges and your nodes are. If you're extracting edges like the word two, like A to B, and two is the edge, then that's, even though if it occurs a lot, it's quite a useless edge. And even if you were to traverse that in the graph, it really means nothing much. So for example, given the very complex problem we saw just now, over here, based off, like for example, this tree, we draw the edges between them. So we can, for example, start candidates, use words to describe them. And I guess this is highly specific to your domain. So for example, in the example, this was a medical document. So you would see a lot of words, for example, upregulates, signals, and I guess this is your call and how you tailor your query extraction system to your database or your data that you have inputted. Next is query decomposition. So I think this is very, very relevant, especially when just like how the first speaker talked about hotpot QA not being mentioned in GraphRAG. It happens to be what my team is working on GraphRAG as well. So what is it really? Just like how you would break down a very complex question into multi-mini questions. You're basically just breaking it down so that you can throw it at GraphRAG, so that GraphRAG can use those new entities and relations in a more, I guess, intuitive way. So for example, for the given example, we break it down to something that is simple and like, I guess, kind of like one step / node and relation kind of process. Plus, it essentially gives you like an execution plan based on what your graph looks like. So I like how it's like a bit like a hotpot, you can say, okay, I want you to make a very nice hotpot. But instead of that, you go to many different people and you're like, oh, I want you to prepare the vegetables, I want you to prepare the meat, I want you to prepare the soup, and that's how you get a hotpot. So yeah, multiple different questions to kind of throw at your GraphRAG system or your retrieval model to follow basically. So next will be query expansion. So on top of that, sure, I might say grab the vegetables to put in the hot pot, but what does vegetables actually mean? There's so many different kinds. So in my opinion, that's what query expansion is really all about. So we want to broaden the search terms with, for example, synonyms, acronyms, or like graph neighbors. So for example, you're kind of not really traversing the graph in the dark, and it's kind of related to your question. So for example, I think there was an example of, for example, the author question. There are so many edges that might come out of the book 1984, but only a few are relevant. So query expansion kind of hints to your retrieval model to say, okay, you should probably look at that direction. And I think here it's where I guess Gen AI and LLM generated content is quite or potentially helpful because it's context aware and it has, I guess, the context of your questions, the questions before that, and here maybe you can make your system even more specific to your domain. So for example, if I just ask Apple Financial 2025, if you just do like semantic search over the word apple, you can't differentiate between the two of them, and my plot is just both. But with query expansion, with extra context, then you have a bit more specificity to what you're searching for. And I think this also ties into traceability. So when you actually look back and you try to see what kind of searches you're throwing at your RAG retrieval pipeline, you know what questions you're asking and you know what to expect as well. Then putting it all together, once again, this is ChatGPT, I guess, summary of what a question, the answer to the, or what you throw at your RAG database or graph might look like. So once again, very domain specific to the kind of RAG you might build, but here you kind of see the different steps kind of play out. So I guess you have your entities, your relations, your subqueries and expansions, and with all of this, your retrieval model might use all of this information to basically traverse the graph and try to get something that is usable. So at the end of the day, it's really a very like sequential progress, sequential kind of step-by-step process, at least outlined by the review paper. So essentially you throw in your very broad, not so clear question, you come up with something which is quite domain specific and tuned to your use, which is your Q-head. I think that's all I have.
Yeah, that's fine. Questions? Estelle has been busy putting up a lot of different questions for us to consider. So if you go back to your Slack space, there are a couple of us that came out that's also been dialoguing. Would ask you to engage questions with your content. So you can ask your own question. So it's about there. Okay. So Hongi really nicely asked ChatGPT for input about how to come up with a query that very decomposition of the processing. Do you guys have any points or reference that you can connect to previous lectures about some of these things? Because many of these points we've heard several times, right? Can you connect any of them to what we're talking about?
Last two I did covered quite extensively because like subqueries and extensions.
Subqueries and expansions, yeah.
For subqueries, like we've seen a few. I think there was I don't remember if it was here or like somewhere else, but like, there was a paper that talked about like how chain of instruct basically uses this to decompose their questions into like step-by-step questions to do like image editing. I believe it was PIC, but yeah, I think it was a paper, but yes, or someone else did that. And then for the expansions thing, I think it was covered in the query router a few weeks ago, right? I think in a sense, this a lot of this is very similar. I think it shows that the concept apply from like the query router to this. But it's pretty much exactly simply just that now this is the purpose of this is to tailor the query for like a graph. So I guess it can be applied quite generally.
Right. So now we're applying the same technologies that we talked about it, all the way from week 2, which is where you're coming from. So we're talking about the query router and deciding whether to do the query expansion, right? To ask again whether it be Apple the company or Apple the fruit or Apple bank, right? Which we put on the right? And then the other part, which is the query decomposition. So I wrote about that in the general panel too, which is to say the decomposition you can think of it a little bit like chain of thought, right? I think most of us are familiar with the idea of chain of thought, picking a large question and asking take step by step with it and decompose parts. So when you do that in the GraphRAG system, then you will have something specific. Why is that? Because your graph has nodes. Your nodes have values. Your edges have classes, right? So then you're constraining your step-by-step thinking to the things that are elements in the graph, right? Either relationships in the graph or so you recontextualize your chain of thought. grounded as that's the terminology there, right? Grounded means you specifically say, don't think about any decomposition. Only think about decompositions of these things that are in the graph, right? So you say, I don't want you to hallucinate things that are not in the graph. I just want you to think about things that are in the graph. Expand something. Another part that we didn't really talk about is the point that many times when we do suspension, we can go back to the user and verify more. Right? So there's this iterative retrieval process that a lot of people study in IR, okay, where you can go back to the user and say, I don't know whether this is good enough to give you some results. I would like to get some more sophistication. So a lot of that happens in recommendation. So for example, in a graph recommenders, for example, recommend movies, you might start by saying, oh, I want to watch a movie. What type of movie do you want to watch? Like what genre? So the genre is a type of attribute of a movie, right? So you say, oh, I like horror, right? And then the system can say, oh, I understand you like horror movies. Well, I can do one of two things. I can already start recommending horror movies to watch. Or I could say, well, the set of horror movies that you could watch is too long, right? There's too many possible things to recommend. So I need to narrow it down a bit. Do you want ones that are recent, or do you want ones that have a star in them, or do you want ones that are rated above a certain level, IMDb or something like that? That can narrow. So this type of iterative process is something that also happens in systems. But in RAG, sometimes we do that computation. I'm sure some of you who've taken databases know that sometimes database systems will basically refuse to run a query because they'll return you too many results. Right? It's like going to give you over 1 million results. Maybe you want to narrow it down. Right? So that type of indexing back of the envelope retrieval first, maybe using a cluster community graph like what Indra said earlier, be helpful, right? So like say from Indra's Leiden clustering that he talked about earlier, you know that community has over 1,000 nodes, then you may not want to return anything in that community because it's too broad, right? Trying to bring that up. Okay. Any other questions, Tao, or anyone would like to give any additional comments? Jonathan?
Sorry, I see that the AER becomes like a foundation or like a safety tier or structure as well, right? In general, it's okay to build AER on the panel, all the understanding of that, right? So, but the reason we do RAG is because for domain specific or maybe here we want to train model, although we try to use the RAG that, but in this case here, the AER does not work so well in the domain specific. Yeah, it has a trained model to get a better, right? So it's a little bit like a chain active.
Yeah, those are very good questions. So if you're starting out with some source material like a corpus, then usually you have enough other text to help disambiguate, right? So sometimes like CRP, for example, on this slide here, right? It could mean anything in some context, right? But here you're only talking about, like upregulation and downregulation of protein. So that specific acronym means something specific. Even within the biological protein, that particular understood means that, right? So trying to disambiguate is a very helpful. Right? So when we try to disambiguate a name that you during retrieval, that's also very tricky, right? So you have to know something about the user, know something about the underlying database of relations in the graph, but help you try to disambiguate. But yeah, maybe you could give more detail on your question.
I mean, you have the proper results for this whole pipelines. Here, the first step is very quick results, right? So, I mean, for very specific domains here, we may not really be against because we have that very good domain kind of LLM, we probably don't need that. Right? So the reason we have to do that is because on the training level, they handle it. And that also gives the constraint. It is the constraints also here at the first steps.
Yeah. So many times we want to move to a knowledge graph because it's a more precise representation of natural language. So it may be that you're favoring precision over recall. And what I mean by that is because when you do the conversion of a text and you do the disambiguation of named entities like CRP, here it stands for a certain C-reactive protein, right? It doesn't stand for whatever else. It might be a conditional random process, which is also CRP. Then you might say, okay, well, in this domain, I'm just going to call that, and it has a particular name entity. It has a particular identifier. So there's more exactness in your specification.
So we use so evaluate problems end up being not very long. As the first step. The foundation problem.
So do you need to craft a good name entity recognition system in order to convert a corpus into a knowledge graph? Generally, probably yes, or you need to have enough domain knowledge about how to ask the questions to convert the text into a knowledge graph. Yeah, so that is the difficult problem.
There might something that might be interesting. I'm not too sure if this is that specifically targeted at this problem, but when I was reading, there was this paper. This one, I think it was about. So basically, I think they were trying to find relations between different name entities, and what they did was they blacked out the entities themselves. So the model kind of learns by looking at the context which things in the corpus are actually the entities, and it picks on that. But honestly, I did not understand this paper well enough to kind of give a good explanation about it.
Okay, so this is a little bit like masking. If you understand how to train a language model to be model plus, we do this all the time. So we take sentences and then we X out some parts. We have the language model try to recreate it, right? If it recreates it well, then we say that's a good example. And so this is how we train language models, right? So if you yeah, it's basically many of those like bottleneck systems where you try to have the system compress the information but recreate it as an identity. Right. So you take a sentence, you blank out words, then you train the system to recreate those words in context, like what the problem says, that you can right. So examples of that would be in Jonathan's context, if you have the word like C-reactive protein bracket CRP, then you can blank out either one of them, right? So you can say, I don't know what CRP means, so I have blank, blank, blank CRP, and the system has to learn that C-reactive protein. On the other hand, you might blank out what's in the parentheses and say, hey, how do you make this into a short form, right? Then you can learn about it. Okay, so we're going to take a 3-minute break, and then we'll come back and Van-Hoang, you're online already, right? I think he can take over share. Okay, so 3 minutes, guys. So there's one way you can take up start.
Prof, can you see my screen?
Yeah, we can. Thanks.
Okay, that's great.
I'll let you know when we get started.
Okay.
Hey. All right. Very good. It's always something else. Before preparing the fund. Oh no, we're trying to oh wow, you do It's not us. Sounds like I just want to start right here. I don't know. What? So you take this one I like. It's I'm gonna do it. Yes, Okay, can you help and all right, so when you're ready, I think you would have an easier time annotating the slide. Can you hear us?
Yes, I can hear you. Okay.
So when you're ready to start.
Okay, sure. Okay, so thank you, Hongyi, for the presentations on the query processor. So next I'll present about the retrieval module of the GraphRAG. So after we have obtaining the process query queue, then the retrieval task is to identify and retrieve the relevant content from the external graph sources in order to produce the context and augment the downstream task generations. So for these presentations, I'll mainly review two types of retrieval, the heuristic-based and the learning-based. So the heuristic-based is typically employs the methods such as entity linking, relational matching, graph traversal, Whereas for the learning-based method, we'll try to learn a better representations of the graph components such as entities and relations. And this is done by representations learning using shallow and deep embedding. So the first paper that I want to discuss is the retrieval augmented generations with graph literature review. So in this paper, they try to give an overview of the three methods: entity linking, relational matching, and graph traversal. So in entity linking, we basically maps the entities in the queries to our nodes in the graph data sources, and this will form the initial bridge between the query and the graph. And in relational matching, we'll try to align the relations that was extracted from the query with the edges within the graph data sources. And after we have obtained the linked entities and also the match relations, we're trying to form like a small subgraph of the large graph. And this can be done by algorithms such as BFS or DFS. So maybe I can give an example here. For example, if the query is what is the nationality of Jack's wife? So first we'll try to do entity linking to identify the main entity here, which is Jack. And then we'll try to link the entity with an entity node in the graph. So in this case, is this node Jack here. And then we'll try to extract the relations in the query. So in this case, there are two main relations, nationality and nationalities and wife, right? So in order to effectively learn from the graph context, we also need to align these relations with the actual edges in the graph. So this can be done by matching the relation nationalities with the edges such as born in or state of, and also the relation wife with an existing edge in the graph such as married to. And then after we have obtained all these entity and relations, we'll try to run some graph traversal in order to extract the connected subgraph. Okay, so the next paper I want to discuss is the KG GPT. That's basically a general framework for reasoning on knowledge graph using LLMs. So for this paper, first, it's try to break down the input queries or sentence into sub-sentences that's corresponding to one relations. And then it tries to link all the entities in each sub-sentences to the KG nodes. And we call this set of linked entities E. And then the author used the LLMs to match the relations within each sub-sentences with one or more KG relations R. So you can see in the figure below, for example, this sentence about William Anders, the framework will extract the entity sets here and also try to break this long sentence into multiple sub-sentences. And for each sub-sentences is try to extract the entity set of each sub-sentence. And then after we have obtained the entities of each sub-sentence, we'll try to retrieve the set of relations that connected to all the linked entities in the knowledge graph. And then this set of relations is combined with the corresponding sub-sentence to establish the prompts for the LLMs to generate the sets of the final top K relations, RIK. And we combine the subgraph made up of all the triples whose relations come from RIK and the entities come from E across all the different sub-sentences. And this will be the context that we use for LM generations. Yeah, so you can also see from the figure, after we have extracted the relations candidates, we will pass them all into LLMs, and we will prompt the LLMs to help us extract the top K most relevant relations. And then we'll combine this top K most relevant relations with the original entities from each subsensus into a connected subgraph, and then we'll pass this into the LM again to output the final answer. So for the test that the author is working on, it's the factual verifications. But after this work was published, the next research also argues that the knowledge graph is not only a factual knowledge source, but it can also be used as reasoning informations. So that's why the next research focusing on how to also use the information provided by KG to improve the reasoning ability of LLMs, such as this work, RAG, or reasoning on graph. First, ROG tries to prompt the LLMs to generate several relation paths that are grounded by the knowledge graph as the reasoning plans. And then from these reasoning plans, it tries to retrieve the reasoning paths from the KG using the plans. And finally, after retrieving the reasoning plans, it tries to conduct a faithful reasoning based on the retrieved reasoning path and then generate the answer. We can take a look at the figure here. The question is, what is nationality of Joe Biden? So first, we'll pass this question into LLMs and then ask it, please generate helpful relation paths for answering the questions. And then the LLMs can generate a few reasoning plans, such as first, we'll try to look at the relationships born in, then city of. Or we can also take a look at graduated from and located in, or professions, then worked in, then city of. And then we'll pass each of these relation path into the planning optimizations. So these planning optimizations will try to ground this reasoning plans into actual reasoning path that exists inside the knowledge graph. And then after we have obtained the reasoning paths, we will create another prompt, such as please answer the questions based on the reasoning paths and explain why. Then we'll pass both the original query and also the reasoning paths into the large language model again to get the final answer. So here is how the author designed the planning modules. Basically, the author introduced a very simple instruction templates. And the questions together with the instruction template is fed into the LM to generate a relation path. So the author used supervised fine-tuning, and the ground truth path is defined as the shortest path between each pair of entities in the questions and the answer. As for the retrieval reasoning modules, the retrieval module retrieves the reasoning path from the KG based on the generated plans. As I mentioned, the original reasoning plans generated by the LLMs may not be valid. So we have to adopt the constrained breadth-first search approach that's try to ground these reasoning plans into actual reasoning paths that exist in the KG. And this reasoning path has to satisfy some conditions, such as it needs to start from the question entities and then follow the relation paths and then reach some existing entities. And the reasoning modules will then take the questions and a set of reasoning paths to generate the answers. And the instruction templates is presented as below. Okay, so There are some problems with the heuristic based retrievers that we have just discussed. So you can see that the LLMs are called too many times for entity linking, for relation matchings, for graph traversals, and for generations. So if you use like some costly LLMs, it will burn through your budget very quickly. So some typical ways that the LLMs are used like TOG, that's think on graph. So it uses LLMs to retrieve the relevant facts hops by hops. So this is the order of complexity is in the order of the branching factor. Or the reasoning on graph method that we just used, it uses LLM to generate plausible relation paths, which are then queried on the KG to retrieve the relevant informations. But you have noticed that the LLMs that use to generate the reasoning path, it doesn't actually consider the graph context. And it's only consider the relations in the graph, but it doesn't consider the actual entity. Yeah, so we want to ask ourselves, is there an efficient but effective methods? Like in the traditional RAG, we have the dense retrieval, but on graph, what are our options? So if you're familiar with graph neural networks, you'll know that it's a very effective method to learn better representations of both the graph entity and also the graph relations. And it's able to utilize the context from distant nodes of the graph. And in this case, it can help improve our retrieval task. So that's why I want to discuss this paper, the GNN-RAG paper that's use graph neural networks for effectively retrieval for graph RAG. So this GNN-RAG, it has two parts. The graph learning phase, that is given a query, the GNN will learn to embed the KG specific semantics and identify the relevant nodes as context. And then it also has a retrieval phase. That's the GNNs will score the answer candidates from the context and then retrieve the shortest paths that connects the questions and the entities and the answer candidates. So first, about the graph learning, we'll try to obtain k different questions embedding for different parts of the questions. So you can think of this as an analogy to the multi-head query attentions. And the query embeddings and the relations embeddings are then encoded via a shared pre-trained language model. So this can be models such as BERT or Roberta, etc. And the multi-head GNN layers, which will aggregate the neighboring messages that's based on the different question parts as the equation below. So I'll try to break down these equations. So first of all, this L here is the current layers of the GNN. So you can see that the next layer of the GNNs, the representation of the nodes is HL plus 1, and it depends on the previous representations of the node, that is HL. And it also depends on the message here. That's basically measure the importance or the strength of the neighboring nodes with the nodes that we are considering. And this message here consists of two parts. First is the node importance score, and second is the relevance between the query and the relations. So, for example, if our query is which language do Jamaican people speak, and here is our graph, then we identify the nodes as Jamaicans, and then here are the four neighboring nodes, each connected to the node Jamaicans with a relation here. So because in this in these functions, right, we'll try to calculate the relevance between the query and the relations, and this will reflect the strength of the connections between the nodes and its neighbor. So in this case, we can see that the query is which language do Jamaican people speak? So it has high relevance with these two relations, official language and language spoken. So the connections between the nodes Jamaicans and the nodes English and the nodes Jamaican English will be much higher than the connections between the node Jamaicans and the nodes other neighboring nodes such as Haiti or Caribbean Sea, which has less relevant relations. Yeah. So after we computed this message passing, then we'll be able to compute the next layer representations of the nodes in our GNN. And because for GNNs, it's typically a stack of multiple layers, so we'll be able to learn like a distance context between nodes and its one hop, two hop, or like n hops neighbors. And we try to initialize the node importance score as a 1 at the first layer, L equals to 0, if V is in the question entity and 0 otherwise. And at each layer, the probability vector is updated based on a learnable weight W here. And this is essentially a parameter of the GNN. Okay, so the effectiveness of GNNs are largely depending on the training data and may not always generalize well to the unseen context. That is why typically we combine GNN RAG with other methods such as the RA reasoning on graph papers that we have just discussed. So the way it does is that given the query, we'll also try to devise the reasoning plans, and then the reasoning plans will also give us a reasoning graph, right? And then we'll try to unify the graph that's generated by the ROG with the graph that are generated by our GNN methods. And then it will helps provide our LMs with much richer context. And not only can we combine the graph that's generated by GNN and ROG, but we can also combine it with the traditional RAG dense retrieval methods, such as text embedding similarity, yeah, and even expand the context of our LLMs further. Okay, so the key takeaways are that we can also consider the heuristic-based method for its simplicity and times resource efficient, entity linking, relations matching, and graph traversal. And the knowledge graphs are not only knowledge sources, but they can also be used for reasoning. And finally, learning-based methods such as GNNs can help us learn better graph representations and improve the retrieve context. And that's all for my presentations. Next, I'll transfer to Louis.
Thank Juan. There are some discussion questions that Dell and others have, so let's take a look at some of those as well. Any comments or questions on this part before we go to the final part? Everyone happy so far? So you know, GNNs are again more akin to transformer models and other they're constant to work on their synthetic. So the GNN RAG methodology I think is less precise, much more dense method for doing these things. It's quite different than the other boring tag architectures that Pongi and others went over in very structured part. Okay, so there's a varying of these two different technologies when you look at something like a network-based RAGs. Okay. Yeah, so we are doing pretty well on time, so we'll go on. Thanks, Van-Hoang, and then Louis, you can take the screen share and mute it. You like you can take time out.
Okay. Check. Can everyone hear me? Okay.
Yes, we can hear you fine. Thanks so much, Luis. Let's start with
Okay. Okay. Thank you. Okay. So hi everyone. My name is Luis, and I'm going to walk you through the last part. And I guess this part will mostly be consists of many examples. And for example, like we are going to first talk about the organizers, and then we are going to talk also about what are the examples for generators, what are the types that we can use, and like what are the strength and weaknesses, and like when should you use every type of generator or organizers, and like what are the people are doing in order to achieve these two modules basically. So I think because this is mostly additional, like for example, if you are working on a rack system, and then if you're working on a naive rack system, you would basically stop after you retrieve something, but this is some sort of optimization after you retrieve your documents or after you retrieve your knowledge graphs. So yeah, basically this will contain a lot of examples, like what are people doing for the specific cases, how they do it, and like what we can take from its examples. And especially because this is two modules of the basically 5 modules that the review paper is proposing, and because mostly they contains examples, I'm really sorry if some of my explanations are quite shallow of the papers, but yeah, I hope you can get something from this part. So the first part is organizer, and this organizer basically we wanna organize how our data is presented after we retrieve it. Like maybe our data is documents, but in this case, our data is the subgraph or the retrieve KG. So how can we organize it so that we can get the most of it? Like how can we get the most performance, or how we get the most information from our graphs? And it can be further categorized into 4 types according to the review. Like there's pruning, re-ranking, augmenting, and verbalizing. And I'm going to give you a brief overview of every one of them and some few examples. So for the first one is pruning. So I guess for pruning is kind of straightforward. So basically you have a graph and you want to prune some subnodes because they are not important. So and this is works well because the retrieve graphs from your KG could be very large and noisy, of course. And those noise could hurt your performance, and also those large graph can also hurt your computational efficiency. So basically, all of the examples from these sections are talking about how do you determine, like, how do you determine which nodes to cut? Or basically, how do you calculate or how do you score its nodes based on the relevancy to their objective or to the questions? So there's also, again, 4 ways to do it that um, that is presented in some of the few examples in the paper, like for example, semantically or structurally or by its syntax or dynamically. So first, this is an example from QAGNN, this paper. This paper actually talks about how you could leverage this concept to help you like answer QA questions. And basically here they are going to first retrieve a KG, and then they are going to prune it further. And how they prune it is that they are going to feed those KG or feed that working graph into a language model. And then that language model is going to give you a relevant score based on the QA context. So for example, maybe the QA context is the questions, and then the answers. So basically, the resulting KG is going to be a really small version of it, or basically a pruned version of it, where you are going to take top n or top something out of the basically the important nodes. So it's very straightforward. You use language model to do it semantically. And this is another example from this paper, ROK paper. So in this paper, they also are doing it with LLM, but in this case, they are not scoring the nodes, but they are scoring the edges. So for example, this edges represents a relationship, and they also first do it by deduplication, the duplicate relationships. For example, maybe R1 here appears 2 times, so you only want like only one of them. So you don't have to do the other ones. So you first deduplicate it, and then you could also semantically score its relationships. So if that relationship is not really tied to your context, then you could just remove it. So you further pruning your graph. And then the next one is structure-based pruning. So what does that mean when we say structure-based? Basically, structure-based meaning that you are going to determine the relevancy score only based on your relationship between nodes and edges. So by the structure of the graph, by the topology of itself. So basically, the most, I think the most, sorry, the most efficient algorithm that many people use is one of them is the PageRank algorithm. And this PageRank algorithm is very versatile. They use it in some applications. One of them is, of course, in searches, in Google search. They also use this in some form. But I'm going to use this explanation by the previous paper, the ROK paper, because the ROK paper also use this PageRank to try to score which node is the most important. And the way they do it is that they are going to calculate PageRank using this formula. But I think the formula is not too intuitive. So if you want to just understand how PageRank works, basically they are going to calculate this part. So PR, EI, entity I, or node I. And then for every node, you are going to consider like what are the nodes that is neighboring your nodes. And basically, if you are neighboring important nodes, those importance score is going to distribute it to you. So this is the sum of like every other node and then the links to the links in that node that is going out. So you are going to distribute the importance of this node evenly towards many outgoing nodes that you have. And then also the teleport term. So if you imagine that this is some sort of algorithm where you would have a server, and those server will try to traverse all of your nodes based on your edges. So like you can imagine that this server is going to perform a random walk. So you would try to visit every nodes, and then based on how often you visit a node, meaning that if the node is often visited, so that node is more important than the others. So of course, and because it depends on how many times you visited it during random walks, so the number of edges you have and how the structure of your neighboring nodes is going to affect how important that node is. And also because it is based on that some sort of trying to serve across or traverse across the nodes, then they also introduce this teleportation term, which basically uh, if you still imagine it by using some sort of server that is traversing the graph, then this teleportation terms means that sometimes there's a little chance that your server is going to basically get bored with your node and it's not going to follow the edges of that node and it's going to teleport into another node even though there's no edges that connecting that those two nodes. And they introduced this basically teleportation term so that you could basically decrease the chance that your server is going to like running in circles in a set of nodes that is highly connected with each other. Because of course, when you retrieve a set of nodes, there are going to be some nodes that highly connected, but there are also going to be some nodes that is dangling. And this is the way how they wanted to like solve that problem. But yeah, basically that is how PageRank works. And most of the structure-based pruning is ranking by a variation of this algorithm. And then the next one is syntactic-based pruning. So in syntactic-based pruning, basically you are going to prune your uh, knowledge graph as usual. But in this case, the relationships between your graph, the relationship between your nodes is actually the syntactic relationships between the content of the nodes. For example, you could take this one sentence and then convert that into a graph by taking every words into different nodes. But then how you connect those nodes is by the relationship for uh, of its words. So for example, which one is the object, which one is the root, which one is the case, which one is the conjunction, and so on and so forth. So basically, after you have completed that kind of graph, then you could do some sort of pruning where, for example, you say, okay, I have this core node, so the nodes that is syntactically further away from this core node is going to be pruned. So that is just the really simple way to do it. And in this paper in PipeNet, they introduced PipeNet where first they are going to construct that kind of node. So for example, they have one QA context, and then using the keywords from that QA context, they are going to make another knowledge graph based on those keywords and also based on the answers of the QA. So like the blue ones are the keywords that is extracted, and then the uh, purple ones are the answers basically. And these green ones are basically they don't only use the keywords that is extracted, but they also do some expanding here. And we are going to discuss some of this expanding technique later. And then basically they are going to count how many hops do you need in order to get to the answers. So basically the nodes that is farther away than the answers, they are going to deem that as not too relevant to the answers syntactically. So they are going to prune those. So it's really similar, but basically here they are determining this importance by how close you are syntactically. And then the last one in the pruning section is the dynamic pruning. Basically, you are doing this over and over again, doing the pruning over and over again in maybe in training or maybe when you reason in your model. And every steps is going to give you a different types of masking or pruning. So for example, in this paper, Join LK, they introduced this some sort of reasoning model where you would utilize dynamic pruning so that you could iteratively make your reasoning path or make your knowledge graph here smaller and smaller when you reason as it progresses from layer to layer. So they are going to stack this like n times. I think the paper states that they stack this about 5 times or so. And basically, at first you are going to have a complete knowledge graph. So maybe you retrieved it, or maybe you have a quite small graph, so you input it directly. But after they got into the GNN layer and the joint reasoning module, they are going to go into this dynamic pruning module, where in this case, they are going to utilize the attention, some sort of attention that they computed here before this dynamic pruning module, and they are going to use those to score which nodes are not too important, depending on what the model is thinking about, or depending on what the model is trying to achieve. So they are going to mask it, and then the masked knowledge graph is going to basically input it into the next layer. So as you progresses into the layers, the deeper you are, the closer you are to the output, your knowledge graph is going to be more and more focused. And I think one of the main advantages here is that you don't have to explicitly say it to the model like how to determine the relevant score or how to determine the important score, and the model is going to just compute that for you based on like its internal mechanisms and based on like what question or what objective that it is trying to achieve here. Okay, so that is all for pruning, and we are going to go into re-ranking. Basically, re-ranking is quite straightforward as well. So it is also quite the same as if you are re-ranking some documents. So I think the term in graph and non-GraphRAG is quite the same. And basically, the motivation to re-ranking is that you have a problem where some positions holds more importance, or basically the model holds some attention bias, especially in if you are doing a long context. And they also cited some key papers like Lost in the Middle, where, for example, the documents that are positioned in the middles, they are really hard to really hard for the model to remember, and basically they are not really easy to retrieve. So basically, you are going to rerun the results with some pre-trained models. I think based on the current landscape that the review paper have gathered, like a lot of the people that is using re-ranker, they are basically training something like cross-encoders or a pre-trained ranker model. Like there is some here and there's some here. So basically, there is many ways you can do this, but basically you train some models to do it. So the next part here is augmenting, so or expanding, like I discussed before with the previous example. So basically, there is two things that you can augment or expand. You can first augment the structure, or you can augment the feature. So of course, the purpose of augmenting is that we want our models to have more information so that it could generate more accurate predictions. But basically, what you want to augment is going to depends on like what are you trying to achieve in your model. So for example, here in feature augmentation, they can use LLM to enrich information of the nodes. For example, your node may be the users, so you can profile the users, you could summarize their contents, and then it's going to sorry, it's going to provide you with more information. So basically you can consider a lot more things in general. But when we are talking about structure augmentation, basically you are going to try to add new nodes and edges to your graph. So this is not the content, but this is the typology or the topology or the structure of the graph itself. For example, in the PipeNet that we discussed before, they are going to use an existing graph like ConceptNet in order to the expand the knowledge graph that they are creating from this QA context. So basically, for example, city may be connected to road, or forest may be connected to hill, wood, and squirrel. So they are going to use an existing graph that people already made to basically expand so that you could host more concepts in your knowledge graph. Or for example, another uh, type of examples that we have here is UniArc from this paper, cross-domain graph data scaling. Basically, it's quite different from the previous example of augmenting, because the previous example basically introduced new nodes connection. So they introduce new nodes. But here in UniArc, they are training a diffusion model to basically generate the topology of the graph itself. So for example, you have one graph that is as the input of the basically as the input of the model. So this one graph would have their nodes and would have the original topology or the connections between it. But then in order to enrich the information that you have between these nodes, and also to help you like uh, to help you answer their questions, or to help you fill in more information, this structure and augmentation part is going to create you more combinations of edges. So it's going to create you more topology for you to use. So in the end, they are going to generate n types of topology, and then you are going to stack them all together and put it as inputs for your downstream tasks. So basically, you are generating graph topology. And then also, this is another example when you would use LLM to generate the content summarizer or user profiler as the previous feature augmentation did. So basically, it is really straightforward. Like you have a content here, you have user profile, and then you are going to transform those information into a better format, or maybe you want to create more instances or more samples. It's quite straightforward. And then next you have verbalizing. So basically, verbalizing here means that you have a KG as your input or as your source of information. But sometimes when you want to utilize that knowledge graph, you would want to convert it into natural language. So maybe you want to use that knowledge graph into a LLM that only inputs like tokens. So in this way, you need to verbalize your knowledge graph first. So basically what people are doing is that there are two types of approaches. So for example, one is linear. So basically, we are going to use linear transformations or very simple transformations in order to make that KG easily representable in tokens. So for example, they are representing in a tuple format or creating something like a prompt template. Like you have a template and then you put in the variables based on your knowledge graphs. Or you can define some model that you fine tune in order to maybe generate some representations that LLM could accept, or maybe generate some actual tokens that the LLM can, again, you paste it on the prompt. And here's an example of the tuple sample. So from this paper, and this paper basically, literally they are pasting it as tuples. For example, the retrieved triples are Alex Linton plays of the New Orleans, and so on and so forth. And basically, they are pasting these tuples directly, like in the context. So basically, there's nothing too complicated here. They just take the tuples and paste that here. And then the next thing is that when you are trying to project your graph as a sequence, and then you use that sequence together with the token embedding sequence. So for example, here in Laga, I think Laga is, the name is, I think, inspired by Lava. So for example, here they have a graph structure, and then those graph structure is going to be transformed into node sequence. And then that node sequence is again going to go into a projector here. And then they are basically is going to be transformed into embedding sequence that is compatible with the LLM. So they can stand side by side with the token embedding that is generated from natural language. And then you can use it as additional context when you do like classification or when you do generation. Okay, so that was it for the first part. And then I guess I'm going to also go briefly in the second part. I think it's going quite late. So for the generator part, basically, after you got all the informations from the retrievals, after you reorganize it, then how do you make predictions, or how do you then answer the questions? Do you generate text or something? And I think the easiest one is, of course, you use LLMs. So after you get your informations in any ways, you port it into a type of representation that LLM can accept, and then you basically give the task to the LLM and generate me something. And the other thing is that you can use discrimination-based generator. So basically, discrimination means that most probably this is not generative use cases. So regression or classification, then you can use this. So this is not too complicated in a way. You don't need to really generate something. And then there's also graph-based. So basically the intuition between graph-based is that uh, if you are trying to port the knowledge graph into other types of representations, you might lose context because in some information they do gain advantage when you represent them in the original way. So basically, graph-based the intuition behind the graph base is that we want the information to stay in the graph representation so that we don't lose context. Okay, so I think we go with the easiest one first, the LLM base. So of course, first you can do verbalizing. This is like the easiest option. Maybe you pasted the text representation of the, you paste the text representation of the graphs and then you ask an LLM to basically, okay, make deduction based on this. Or maybe you first, okay, please make a paragraph out of this knowledge graph and then you can use it as context. So it's really straightforward. And then the next thing is embedding fusion. So basically you are going to transform the graph structure into the embedding and jointly making predictions with text and graph embedding. So it's really quite similar to this, but this is a different paper that is giving us the example now. So they are terming this as graph neural prompting, but I think the principle is quite the same with the previous one. So basically here you are going to have some subgraph retrieval. So you're going to have some options here. You extract the subgraphs and it is going to go through this component that they are making here in this paper, graph neural prompting basically. They name it GNP. And basically they are going to go through an encoder and these encoders is going to transform them into embeddings, and then those embeddings is going to go through cross-modality pooling, and then you would have more embeddings, and then the domain projector is going to make sure that it is compatible with the text embedding that you are going to use it. So basically, it's quite the same in principle, but they are using different components, like they are using the separate encoder, they are using the cross-modality pooling. So I believe the approach that they are going here is more of a looking of graphs as another type of modality. So I think that is an interesting perspective of viewing graphs as a different modality. So, but in the end, the end goal is here is quite the same with the previous one, that you want a representation of the graph that is also compatible with the text embedding, and so that you can use them side by side to generate something or to make predictions. Okay, so, and then for the discrimination base, basically, as I said before, they are going to focus on discriminative or regression tasks. And all of the examples that is present here today is mostly when you integrate graph with some other types of architecture. For example, graph convolutional network, where I believe they are doing some sort of convolution, but because it is not pixels, you need to have some creative ways in order to make that work. And then also graph transformers, when you are combining GNN with transformers, and there's actually many ways you can do it. Like for example, this is from the paper graph transformers, this paper transformers for graphs. And basically there are many ways to do it that they presented here. Like you could have your input go through GNN first and then transformers like basically before, or you can have it do alternatively. So first GNN and then second go to the transformers block and then so on and so forth. So basically one layer it consists of GNN and transformers block. It could be structured like this, or maybe also side by side, like you are inputting, you are diverging the input into two parts, transformers and the GNN, and then somehow you are going to again have to jointly compute the two representations into one, maybe using a projector or a pooling layer between different cross modality. So I guess again there is a lot of ways you can do this. So I believe it's okay if we just go through with the general concept, because you can be creative with basically every type of configurations here between graph and transformers, or with CNN, or with something else. And then for the graph base, again, this is, as I said, they want to preserve the graph structure, because for example, in scientific literature or in scientific applications, you don't really want to lose that information from the graph structure. for example, like the red mole here. This is, I think, the molecular retrieval for molecular thing that we are discussed throughout the presentations today. So basically here they are going to have an input molecule, and this input molecule basically is represented by a string, if I'm not mistaken, a smile string. And then you are going to retrieve more exemplar here, and then you are going to encode them separately. But the encoder is going to share with. And basically this encoder and decoder are supposedly basically they are specialized to accept these kinds of sequences. So you don't really want to lose context by using any types of other encoders. So they are preserving its structure here by using a specialized encoder. So, and then you are going to fuse information, and then the decoder is going to make predictions or make the output molecule here. And I think it's also quite interesting that you could have different sequences, because I think we are focused on text as sequence, but in the real world, there's a lot of things that we can represent as sequence. So this is one example. Okay, so I think that is the last slide of my presentation. I hope it is not too late. And yeah, that is all for me. Thank you, everyone.
So because it's quite long now, I think we'll end our session here. So next week we have our final part on Van-Hoang source credibility. Be able to assess which parts of the RAG refusion is credible. So I'll just invite whether Haifao or Alex have any input. If not, I think that's it for today. So thanks so much for coming. So we'll see you next week. Yep. Thank you. Thank you all for listening.